Up to this point, we have examined motion in the upper ocean driven by wind and shaped by Earth's rotation. Surface currents redistribute heat and organize into gyres. But that is only part of the story. Beneath the wind-driven layer lies a much larger reservoir of water that moves for entirely different reasons. Deep ocean currents are not driven by wind, but instead they are driven by density differences. Those density differences are controlled by temperature and salinity, properties you already understand from earlier in the unit. Today, we will build how density changes cause water to sink, how that sinking spreads across ocean basins, and how the entire ocean becomes connected through slow overturning circulation. Deep ocean circulation begins with density. Density determines whether water sinks or rises under gravity. If one parcel of water is denser than another, gravity is going to pull it downward. In seawater, density depends primarily on temperature and salinity. Water molecules move more vigorously at higher temperatures. As molecular motion increases, the average spacing between molecules increases slightly. This means that for a given mass of water, warmer water occupies slightly more volume. Increased volume at constant mass means lower density. When water cools, molecular motion decreases and molecules pack more closely together. That decreases volume and increases density. So colder seawater is denser than warmer seawater. When salts dissolve in water, they dissociate into ions: sodium, chloride, magnesium, sulfate, and all the others. These ions add mass to the water. While dissolved ions also influence water structure slightly, the dominant effect is that salinity increases mass more than it increases volume. Therefore, increasing salinity increases density. So the rule for deep circulation is straightforward. Cold and salty water will sink. Unlike surface currents, which are driven by wind transferring momentum, deep currents are driven by buoyancy forces. If a parcel of surface water becomes colder or saltier, its density will increase. When its density exceeds that of the underlying water, the water column becomes gravitationally unstable. Gravity then forces the denser parcel downward. This is the fundamental difference between surface currents and deep currents. Surface currents are momentum driven. They started from wind. Deep currents are buoyancy driven due to density differences. Everything in this lecture builds from that one principle. Density differences create vertical motion. Now that we understand that density differences drive deep motion, we must ask a mechanistic question. How does surface water actually become dense enough to sink? Surface water does not randomly increase in density. It requires specific environmental processes. There are three main processes that drive this. In high latitude regions, particularly during the winter, surface water loses heat to the atmosphere. This occurs through sensible heat floods, direct transfer of thermal energy to colder air, as well as through latent heat floods via evaporation. As heat leaves the water, its temperature decreases. As temperature decreases, of course, density increases. If cooling is strong enough, the surface water may become denser than the water beneath it. When water evaporates, only pure water molecules leave the surface. Salt does not evaporate. This means that evaporation removes fresh water but leaves dissolved salts behind. So as evaporation proceeds, salinity increases. And as we know, as salinity increases, density increases. The third process is sea ice formation. When seawater freezes, the crystalline structure of ice excludes most dissolved salts. The salt does not enter the ice lattice efficiently. Instead, it is expelled into the surrounding liquid water. This process is called brine rejection, that increases salinity and increases density. Now imagine winter conditions in polar seas. Air temperature is low. Heat flux from ocean to atmosphere is high. Sea ice forms and rejects salt. Surface water becomes both colder and saltier. These processes act together. If surface density exceeds subsurface density, a gravitational instability develops. This leads to convective overturning. Convective overturning is vertical mixing driven by buoyancy forces. Denser water sinks, lighter water rises to replace it. Unlike wind-driven mixing, which is limited to the upper ocean, convective overturning can extend much deeper when density differences are large. Deep water formation begins here, with surface buoyancy loss. Deep water does not form uniformly across the global ocean. It forms in very specific geographic regions where the necessary density conditions are met. There are two primary deep water formation regions in the modern ocean. One is the North Atlantic. The second is the Southern Ocean surrounding Antarctica. You can see those labeled on the diagram to the left. In the North Atlantic, particularly in the Labrador Sea and Nordic seas, winter air temperatures drop dramatically. Cold continental air masses move over relatively warm ocean water. The temperature gradient drives intense heat loss from the ocean to the atmosphere. The Atlantic generally has a higher salinity since it receives less freshwater river runoff than other oceans. Higher salinity means that density increases even quicker as the water cools. As a result, surface waters in these regions can become dense enough to sink to depths of 2,000 to 4,000 meters. This sinking forms what is called the North Atlantic deep water. Likewise, around Antarctica, intense sea ice formation during winter leads to brine rejection. As ice forms and excludes salt, surrounding surface water becomes very saline and therefore very dense. This dense water sinks and forms Antarctic bottom water. Antarctic bottom water is among the densest water masses in the global ocean and can flow along the ocean floor into multiple basins. These two formation regions are the primary engines of deep ocean circulation. It is critically important to remember deep water formation requires three things: strong cooling, high salinity, and limited freshwater dilution. When these conditions are met, sinking initiates deep ocean flow. When dense water sinks, it does not fall endlessly. It descends through the water column until it reaches a depth where its density matches the surrounding water. Instead of continuing downward, the water begins to move horizontally along surfaces of equal density. These are called isopycnal surfaces, surfaces along which density is constant. When water sinks in one region, mass accumulates at depth. The ocean must redistribute that mass, pressure gradients develop at the depth, and water flows away from the formation region. This flow is slow compared to surface currents. Instead of tens of centimeters per second, deep currents often move only a few centimeters per second, but they are persistent. A surface current can cross an ocean basin in years. A deep current may take decades or centuries to complete its pathway. North Atlantic deep water sinks and then flows southward along the western Atlantic basin. It eventually reaches all the way to the Southern Ocean, where it interacts with the Antarctic bottom water. From there, deep water can spread into the Indian and the Pacific Oceans. The slow spreading connects ocean basins and redistributes heat, oxygen, and dissolved substances throughout the deep ocean. What begins as localized sinking becomes basin-scale horizontal spreading of extremely large volumes of water across all oceans. Remember, our first week of class, we talked about all ocean water being connected and operating as a single system. Well, here we are. The density-driven circulation is why. Let's now go back to review the basics and make sure we understand why deep water formation occurs only in certain regions like the Southern Ocean and the Northern Atlantic. To do so, we must understand stratification. Stratification refers to the vertical layering of water according to density. In most of the ocean, lighter water overlies denser water. This configuration is gravitationally stable. If a small parcel of water is displaced downward, it finds itself in denser surroundings and experiences an upward buoyant force. It returns to its original position. That is stability. This layered structure resists vertical mixing. Now imagine the opposite condition. Denser water above lighter water. This configuration is unstable. If a dense parcel is slightly displaced downward, it finds itself in lighter surroundings and continues to sink. The system overturns until stability is restored. In other words, deep water formation requires destabilization of the surface layer, and that destabilization occurs in the North Atlantic and in the Southern Ocean. In subtropical regions, strong solar heating warms surface water, and evaporation increases salinity. Even though evaporation raises salinity, the strong heating keeps surface water relatively warm and therefore buoyant. The water column remains stratified. In polar regions, intense cooling removes heat faster than salinity decreases. Combined with brine rejection during sea ice formation, surface density can increase dramatically. When density exceeds that of the underlying layer, stratification breaks down. Convective mixing can then penetrate deeply. Remember that wind can stir up the ocean's surface and can even reach down to a few hundred meters deep during big storms. But wind is not enough to overturn the entire water column, as density differences can. Away from the deep water formation zone, density will generally increase with depth below the surface under the wind-mixed layer, as you see on the illustration on the slide. So now we can put all this together. The combined density-driven deep water circulation is called thermohaline circulation. Temperature and salinity together determine density, and those density differences drive vertical motion and then horizontal spreading. The overturning circulation connects the Atlantic, Pacific, and Indian Oceans into a global system that pulls surface water to deeper depths that then spread across the ocean basins, where it will eventually return slowly to the surface at those upwelling sites we spoke about before. The entire cycle takes hundreds of years to complete. And this is a critical point to stress. When sinking today, water sinking today may not return to the surface for centuries. This slow timescale allows deep circulation to store heat and carbon. And that, of course, is carbon absorbed from the atmosphere when the water was at the surface. Recall that carbon dioxide enters the ocean through air-sea gas exchange, a process you learned earlier in this unit. When cold water forms at high latitudes, it is particularly effective at absorbing CO2 because gas solubility increases at lower temperatures. When that water sinks, it transports dissolved carbon into the deep ocean. Once isolated at depth, that carbon may remain there for centuries. The ocean also absorbed most of the excess heat associated with global warming. Some of that heat remains near the surface, but much of it is transported downward through deep circulation mixing. So this deep water system serves as a large thermal reservoir. Unfortunately, it is still sensitive to change and represents one of the tipping points climate scientists have been trying to warn us about. As warming waters result in faster rates of sea ice melting from glaciers, more fresh water is put into the system, and that lowers the salinity at these deep water formation sites. If the density then does not increase enough to trigger sinking, then the deep water formation weakens and the circulation can slow down. Scientists are already documenting some level of slowing down. Imagine what it will do to weather across the globe if this circulation system completely shuts down. Imagine what would happen to ocean productivity and our ability to catch fish for food. The outcome of such a scenario would be devastating to human survival on this planet. At the risk of sounding repetitive, I want to carefully drive home the point that it would be a mistake to think of surface and deep currents as two independent systems. Of course they are connected. Surface currents transport warm water toward the poles. For example, the Gulf Stream in the Atlantic moves warm tropical water north into the North Atlantic. As that warm water moves toward the poles, it's going to cool, and that cooling increases density. In high latitude regions, that same water may lose enough heat and potentially increase salinity through evaporation or ice formation to become dense enough to sink. So surface circulation drives the raw material for deep water formation. Now reverse this perspective. When deep water forms and sinks, surface water must replace it. That replacement occurs through large-scale surface and intermediate circulation patterns. Deep circulation influences surface circulation by altering density gradients, which affect pressure gradients in current structure. So this is a coupled system. Surface currents are momentum driven by wind but redistributes heat and salt. Deep currents are buoyancy driven but redistributes density and mass. The full ocean circulation system is therefore a combination of wind forcing and buoyancy forcing. Neither alone can explain the observed structure of ocean motion. So it is important to understand that surface and deep circulation are two branches of a single connected system. The focus of this unit is water. Water as a physical structure and now as a collective material that connects all oceans into a single unit. And of course, as a medium that interacts with the atmosphere. A lot of the energy that is pulled into the system in the forms of waves, currents, and even tides is realized at the shorelines. Shorelines are not static boundaries, as we touched on at the end of the lecture on waves. For the rest of this unit, we will explore coastlines by first talking about shoreline dynamics in a little more detail from what we started in the waves lecture. And then we will finish with a discussion about coastal habitats as we transition to our third and final unit of the course, a unit that will focus on the biological aspects of our ocean.